Hello and welcome to Math Zone African Motives. In this tutorial, we will be working through a question on angular motion. Our objective is to solve 4 multiple-choice questions related to angular motion, power, and efficiency. By the end of this video, you will be able to 1. Calculate angular displacement and angular velocity. 2. Determine rotational power. And 3. Apply the concept of efficiency. Let's dive into the first part of the question. Our first question, labeled 2.1, asks, a blue racing car of mass 1.5 tons races around a circular path of diameter 11,000 centimeters at a speed of 120 kilometers per hour and covers a distance of 25,000 millimeters. The angular displacement of the car is a 0.835 rad, b 0.524 rad, c 0.355 rad, d 0.455 rad. The key concept here is angular displacement. Angular displacement, represented by the Greek letter theta, measures the angle an object rotates around a central point. The formula we'll use is theta equals s over r, where s is the arc length or distance covered, and r is the radius of the circular path. Let's first list the given values, highlighting them in blue. The diameter is 11,000 centimeters, and the distance covered, or arc length is 25,000 millimeters. Notice the inconsistent units. We must convert everything to meters to solve this. The first step, highlighted in red, is to calculate the radius from the given diameter. The radius r is half the diameter, so r equals 11,000 centimeters divided by 2. This gives us 5,500 centimeters. Next, we convert this radius to meters. We know that 100 centimeters equals 1 meter. So, to convert 5,500 centimeters to meters, we divide by 100, which gives us a radius of 55 meters. Now let's convert the distances from millimeters to meters. 1 meter is equal to 1,000 millimeters. So, we divide 25,000 by 1,000, which gives us a distance of 25 meters. Now we have both s and r in the correct units. Let's calculate the angular displacement. Using the formula theta equals s over r, we substitute our values. 25 meters divided by 55 meters. This results in approximately 0.4545 radians. Rounding to 3 decimal places, the angular displacement is 0.455 radians. Comparing this to the options, we see it matches option D. So, the correct answer for 2.1 is D, which is 0.455 radians. We have successfully used the arc length formula to find the angular displacement. Now let's move on to question 2.2, which builds on our previous calculation. The question asks for the angular velocity of the car. Angular velocity, represented by omega, is the rate at which an object rotates or revolves. It's the angular equivalent of linear velocity. We have 2 main formulas for angular velocity, highlighted in red. The first is angular displacement divided by time. Omega equals theta over t. The second relates it to the linear speed v and the radius r. Omega equals v over r. Let's use the second formula, omega equals v over r, as it's more direct with the information provided. First, let's identify the given linear speed, which is 120 kilometers per hour. The linear speed v is 120 kilometers per hour. We'll highlight this in blue. Just like before, we need consistent units. We must convert this speed to meters per second. To convert from kilometers per hour to meters per second, we divide by 3.6. So, 120 divided by 3.6 gives us a speed of approximately 33.353 meters per second. Now we have our speed in meters per second, and from the previous question, we know the radius r is 55 meters. With v equals 33.333 ms and r equals 55 ms, we can proceed to calculate angular velocity. Using the formula omega equals v over r, we plug in the values. 33.33 divided by 55. This gives us approximately 0.60606 radians per second. Rounding to 3 decimal places, the angular velocity is 0.606 radians per second. This matches option B. The correct answer for 2.2 is B, which is 0.606 rad/s. We have successfully found the angular velocity using the linear speed and the radius. Let's move on to question 2.3, which introduces the concepts of torque and rotational power. The question describes a machine with a torque of 230 Newton meters at its spindle. The spindle's diameter is 70 centimeters, and its rotational frequency is 13.5 radians per second. We need to find the power exerted. The key formula here is for rotational power. The rotational power P, expressed in watts, is equal to the torque T in Newton meters multiplied by the angular velocity U in radians per second. Let's identify and highlight our given values. The torque, tau, is 230 Newton meters, and the rotational frequency, which is another term for angular velocity, omega, is 13.5 radians per second. The diameter of 70 centimeters is extra information not needed for this specific power calculation. We can directly substitute these values into the power formula. P equals 230 times 13.5. Performing this multiplication gives us 3,105 watts. The options are in kilowatts, so we need to convert our answer. We know that 1,000 watts equals 1 kilowatt. So 3,105 watts divided by 1,000 gives us 3.105 kilowatts. This matches option A. The correct answer for 2.3 is A, which is 3.105 kilowatts. We calculated rotational power using torque and angular velocity. Finally, let's solve question 2.4, which deals with efficiency. The question states that the efficiency of the machine from the previous problem is 90%. We need to find the input power of the machine. Efficiency is a measure of how effectively a machine converts input power into useful output power. The formula for efficiency is the output power P out, divided by the input power P in, all multiplied by 100 to express it as a percentage. From the previous question, the power exerted by the machine, 3.105 kilowatts, is its useful output power. So we have an output power of 3.105 kilowatts and an efficiency of 90%. We are looking for the input power, P in. These are our given values, highlighted in blue. Let's rearrange the efficiency formula to solve for input power. Dividing both sides by P in, we get ETA times P in equals P out times 100. Then dividing by ETA, we find that the input power equals the output power times 100 divided by the efficiency. Now we can substitute our values into this rearranged formula. P in equals 3.105 times 100, all divided by 90. This gives us an input power of 3.45 kilowatts. This matches option C. The correct answer for 2.4 is C, which is 3.45 kilowatts. We have successfully used the efficiency formula to determine the input power required for the machine. Let's quickly review the memo and correct any discrepancies. The memo provided is 2.1 is D, 2.2 is B, 2.3 is A, and 2.4 is C. Let's compare these to our own calculations. For question 2.1, we calculated 0.455 radians, which matches option D in the memo. This is correct. For question 2.2, our calculation gave 0.606 radians per second, which is option B. This also matches the memo. Correct. In question 2.3, we found the power to be 3.105 kilowatts, which is option A. This matches the memo as well. Correct. And finally, for question 2.4, we calculated the input power to be 3.45 kilowatts, which is option C. This also matches the memo. Correct. It appears all the answers in the provided memo are correct and align with our step-by-step calculations. There are no discrepancies to correct. Let's summarize what we've accomplished in this tutorial. We've successfully solved all 4 questions on angular motion, power, and efficiency. First, we learned that calculating angular displacement requires consistent units, and we must convert distances and radii to meters. We used the formula theta equals S over R to find the angular displacement. Second, we saw that angular velocity can be found using the linear speed and the radius. The formula omega equals V over R allowed us to calculate the angular velocity. Third, we applied the formula for rotational power. We used P equals tau times omega to find the power exerted by the machine. And fourth, we used the concept of efficiency to determine the input power. The rearranged formula for input power, P in equals P out times 100 divided by the efficiency, was the key. Thank you for joining Math Zone African Motives. If you found this tutorial helpful, please consider subscribing for more educational content. Until next time, subscribe for more tutorials from Math Zone African Motives.